Okay, let's unpack this. When you go to a really fancy restaurant, they usually hand you this beautiful, heavy, glossy menu.
Oh, yeah, the ones with a really thick paper.
Exactly. And the descriptions on there are just incredible. Everything is, farm to table, ethically sourced, artisanally crafted. It all sounds absolutely perfect.
Right, but that menu is basically the marketing department's dream. It's not the reality.
Exactly. If you really want to know what you are about to eat and how it was actually prepared, you don't read the menu. You sneak into the kitchen, you check the walk-in freezer, and you read the health inspector's report.
Because the kitchen, the actual assembly line of the food, that is the undeniable reality of the entire operation.
And today, for this deep dive, that is exactly what we're doing with the whole concept of AI governance. We're walking right past the marketing fluff.
Which there is a lot of these days.
Oh, definitely. We're ignoring the polished slides and the flashy demos of AI tools that promise you, complete privacy and unbreakable security. Instead, we are sneaking into the kitchen.
We are looking directly at the raw blueprints.
Yes. Specifically, we are exploring the source code of a system called SYRAG. Now, for you listening, just to give you some quick context here, SYRAG is a self-hosted AI operating system.
Meaning it's designed to run entirely on your own hardware.
Right. It manages everything from text generation to document retrieval right there on your machine. And we have a stack of documents here from its code base, the core and ecosystem dashboards, the config files, and the architecture docs.
Which is quite a lot to go through.
It really is. But our mission today is to understand how concepts like trust and privacy aren't just promised in a terms of service agreement, but are actually written into the code itself.
And that distinction between a promise and a coded reality is absolutely vital. This deep dive is about understanding not just what SYRAG does with large language models or LLMs, but why the underlying architecture is built the way it is. We're looking at how specific undeniable lines of code guarantee certain operational realities. Because, anyone can write a privacy policy. But enforcing that policy mathematically at the infrastructure level, that's an entirely different discipline.
So let's start at the very foundation then. According to the architecture documents we have here, that foundation is the core dashboard.
Yes, the core is where the heavy lifting happens.
And the SYRAG Architectural Foundations document makes a really bold claim right out of the gate. It says the system is built as a living demonstration that AI can be transparent, context verifiable, and trustworthy.
Which is a huge statement to make in code.
Yeah, and the intelligence layer, like the actual brain of the operation, doesn't even live in the user-facing web dashboard that you would normally click around on. It lives entirely isolated in the core.
Which really tells us everything we need to know about their design philosophy from day one.
Yeah.
If SYRAG fails technically, it doesn't just fail as a piece of software that needs a quick bug patch. It fails as a proof of concept that true AI governance is even achievable at all. That level of heavy responsibility is baked into every single design decision we are going to look at today.
It's high stakes.
Very. Take the local versus online setting in SYRAG. In most applications, that's just a user preference toggle, like choosing dark mode or light mode. But in this system, it is a hardline operational guarantee.
It's like the blast doors on a submarine. The integrity of the entire vessel depends on those doors doing exactly what they are supposed to do under immense pressure with zero exceptions.
That's a great way to put it.
Because if a section floods, that door has to hold, or the entire sub goes down to the bottom of the ocean. There is absolutely no room for, the door mostly worked.
And you can actually see those specific blast doors coded into a module called lowmetterface.py. This file acts as the primary bouncer, really. It's the strict gateway for any queries entering the system.
Okay, so how strict is this bouncer?
Well, the documentation inside this class explicitly states a rigid hierarchy. Priority 1 is an engine called Llama, which is the local inference engine.
So that runs everything locally.
Right. That means it runs the AI right there on your machine, utilizing your local graphics card, or GPU if you happen to have one. Priority 2 is a service called OpenRouter, which acts as the cloud fallback.
And reading through this file, it doesn't just blindly hope you have the right hardware to run things locally, right? I see a lot of aggressive hardware checks here. It's actively interrogating the machine.
Oh, very aggressively. It runs specific detection scripts to map out your exact hardware landscape. For instance, it uses a command called LSPII.
Okay, LSPI, yeah.
Yeah. To put that simply, it's basically the software shouting out to your computer's motherboard, asking for a roll call of every single chip plugged into it. It's specifically looking for AMD hardware, It also looks for ROCM environments and PyTorch HIP.
Wait, let's pause there for a second for the listener. What exactly are ROCM and PyTorch HIP? Like, why does the code even care about them?
Good question. Historically, AI has been heavily optimized for NVIDIA graphics cards. ROCM and PyTorch HIP are essentially translation layers.
Oh, see.
They allow AI models to run efficiently on AMD graphics cards instead. By actively searching for these, the code is basically proving that it's designed to run locally on messy, real-world hardware.
Like an older AMD-based laptop or a mini PC?
Exactly. Not just pristine, high-end servo farms.
Yeah.
But the most revealing part of this LUM interface module is the routing log.
Right, the logs?
Yeah. If you are operating in local mode and your local Alama engine fails for some reason, the system logs a very specific error. It says, Alama query failed, local mode, no automatic fallback.
Wait, I have to challenge this rigidity for a second here.
Sure.
Wouldn't a user actually want the system to just magically work behind the scenes? Let's say I'm working on a tight deadline and my local machine hiccups because I'm out of memory or whatever. Why wouldn't I want the software to just silently route my question up to the cloud so I get my answer without interruption?
I get that.
Isn't a seamless user experience kind of the whole point of good software?
This raises an important question about what good software actually means in the context of data sovereignty.
Okay.
In a standard consumer app, say a streaming service or a social media feed, yes, seamlessness is the ultimate goal. You don't want the user to notice a glitch. But in a governance-first system, silent fallbacks are a critical, catastrophic vulnerability.
Really? Catastrophic?
Think about the implications. If you are processing highly sensitive proprietary corporate data or maybe personal medical records under the strict assumption that it will not leave your physical laptop.
Oh, right.
If the system silently routes that data to a cloud server just to avoid showing you an error message, your system just caused a massive data breach, purely for the sake of user convenience.
Oh, wow, yeah, when you put it like that, the system failing out loud and literally refusing to help you is actually a feature. It's not a bug.
Exactly. Policy is enforced, not bypassed. If you configure the mode to local, you get local. If it fails, it stops and tells you it failed. It does not make independent governance decisions behind your back just to save you a few seconds.
Here's where it gets really interesting, though, because if the system absolutely refuses to silently use the cloud when it's in local mode, what actually happens when things go wrong? Like, does the entire dashboard just crash to a blue screen?
You would think so, but no.
Right. Looking at the code, the answer is no. It has this incredibly highly engineered local safety net.
Yeah, we see the mechanics of that safety net in the lmanager.py module. The developers actually left a very explicit title in the comments of this class.
What did it say?
It says, Unified LLM Interface with Automatic Fallback Chain. All 100% local, zero internet required. And then it outlines a rigorous 5-step fallback chain just to keep the system alive.
Walk us through those 5 steps, because it really shows how hard the system fights to keep your data local.
Sure. Step 1 is prepending the ERG context. RAG stands for Retrieval Augmented Generation.
Right.
Imagine giving the AI an open textbook to read before it answers your question, ensuring it uses your specific documents.
Okay.
Step 2 is attempting to run a program called Text Generation Weibui, which tries to leverage your local GPU for really fast processing.
But what if that fails?
Right. If your GPU crashes or runs out of memory, it smoothly transitions to Step 3. It falls back to a llama running on your local CPU. It will definitely be slower, but it will still work.
Okay, but what if the CPU gets overwhelmed too? Like, what if the computer simply cannot generate AI text at all?
That brings us to Step 4. If text generation fails completely, the system falls back to a RAG-only local search.
Interesting.
It basically stops trying to be a conversational AI and instead acts like a highly secure local search engine, just handing you the raw documents that match your query without synthesizing them for you.
And what's the final step?
Finally, Step 5. It tries OpenRouter in the cloud, but that step is explicitly marked in the code with the qualifier internet required. It is the absolute last resort, and it only triggers if you, the user, have explicitly given the system permission to leave local mode.
It completely reminds me of a cascading hospital power grid.
Oh, that's a good comparison.
Right, because if the main city grid goes down, the hospital doesn't just go dark. First, you try the main heavy-duty diesel generator. That's your GPU.
Yep.
And if that generator refuses to start, you fall back to the backup generator, which is your CPU. If that backup fails, you have localized battery reserves just to keep the life support monitors on, and that's your offline document search.
Exactly.
And only as an absolute, desperate last resort do you try to tap into a neighboring city's grid.
It is an architecture built for true resilience. It's engineered for real operational environments where internet connectivity might be completely severed or deliberately turned off, and yet the system still has a mandate to deliver value to the user.
And this strict logic isn't just in the code flow, right? It actively changes how the system interacts with your data based on the mode it's currently in.
Yes, it adapts.
I was looking at the systemconfig.yaml file, and there is a really subtle detail here about context windows. It actually dictates the size of the context window based on your connection state.
Right, the local versus online limits.
Yeah, it explicitly says local context docs is 5 and online context docs is 8. Why would it deliberately limit the local system to 5 documents but allow the online system to read 8?
What's fascinating here is that the system isn't just flipping a dumb switch between local and cloud. It is dynamically aware of its own physical constraints.
Oh, so.
You see, in large language models, the context window is essentially the AI's short-term memory. But memory isn't free. LLMs use something called intention mechanisms, which have a quadratic memory cost.
Quadratic? That sounds expensive.
It is, meaning if you double the amount of text you feed it, the memory required to process it doesn't double, it quadruples.
Oh, what?
Yeah. The system knows that a local 8 billion parameter model running on your personal hardware will likely choke and crash if you feed it too much context at once.
So it puts a speed limit on itself?
Exactly.
Oh.
It intelligently tunes the retrieval strategy, limiting the context to 5 documents locally to ensure stability. But if it's routing to a massive cloud API with massive server farms behind it, it safely expands that context to 8 documents.
It's smart enough to know its own physical limits, and this deep modularity goes even further. When you look at servicecontainer.py, which is the file that handles all the system's dependencies.
The backbone of the system.
Right. There are 9 different services registered there, but they're registered in a very deliberate order. First is the certificate manager, then the hardware detector, then configuration, memory, the database layer, and the actual LLM interface is only step 6.
It's buried in the middle.
Yeah. It is sandwiched securely after all the hardware and databases, and right before the search engine.
That specific ordering is critical for anyone trying to understand AI architecture. It proves that this is a truly service-oriented design applied to AI governance.
How does step 6 prove that?
Well, by forcing the LLM to be step 6, the system guarantees that the AI itself is not the foundational layer. The security certificates, the hardware detection, the strict database access rules, those are the foundation.
I see.
Because of this architecture, you could completely rip out the AI brain and swap in a new one without breaking the system's underlying nervous system.
So what does this all mean for you, the listener? If the AI is way down at step 6, does this suggest that in a truly secure system, the LLM itself actually isn't the center of the universe?
That is the exact takeaway. The LLM is merely a component.
A very popular component right now, but still just a component.
Exactly. It is a highly capable, very flashy component, but it's just one module sitting inside a much larger sequence. If an organization builds their infrastructure, treating the AI model as the center of their universe, their governance and security will constantly be playing catch-up.
That makes total sense.
By decentering the LLM, SYRAG ensures that the strict rules of the system apply to the AI, rather than letting the AI dictate how the system behaves.
That is a massive paradigm shift compared to how these tools are usually marketed. Okay, so we've seen the heavy machinery of the core dashboard. But if the core is mathematically locked down to be local first, what happens when a user wants to do something inherently messy?
Like what?
Like pulling in images or automating tasks. Let's look at how this translates to the user-facing side, the ecosystem dashboard.
The transition to the user ecosystem is exactly where we see if these rigorous principles actually hold up under everyday use.
Right. Does it survive contact with the user?
Exactly. And looking at the active runtime configuration, specifically the ecowindow.shile, we see the exact same local-first reality. The active environment specifies a llama, running the llama 3.1 8 billion parameter model, explicitly targeted at a local host endpoint.
Meaning it's running right there on the physical machine, isolated from the web.
Yes.
And if one of those ecosystem tools breaks, the configmanager.py file handles missing services beautifully. Instead of throwing a fatal error and crashing the whole user dashboard, it logs missing services as optional. The system degrades cleanly.
Graceful degradation is a hallmark of mature software design. But returning to your point about expanding beyond simple text generation, let's examine the image service.py module.
Oh yeah, the image generation.
It follows the exact same data sovereignty rules as the text engine. It supports 4 different image generation backends, but the local ones are strictly prioritized.
So it tries to build the image locally first.
Yes, it is programmed to run local stable diffusion via a tool called Automatic 1111, or even generate local vector graphics directly through a llama, long before it ever considers reaching out to cloud providers like Gemini or OpenAI.
It's like having a universal remote for your entire digital life. The exact same local-first governance model flawlessly controls your text generation, your image creation, and even your automated email blasts.
The newsletter integration is fascinating.
Right. I was amazed looking at the newsletter integration.py module. It actually recommends and defaults to a local setup. It bypasses third-party email APIs like MailChimp or SendGrid entirely.
Yes, it establishes a local SQLite database to manage the subscribers and uses cron jobs paired with direct SMTP.
Let's translate that for the listener real quick. Cron jobs are essentially digital alarm clocks for your computer, telling it to run a specific task at a specific time.
Right.
And SMTP stands for Simple Mail Transfer Protocol. It's the Internet's standard fundamental mail delivery system.
Precisely. By using cron jobs and direct SMTP, the system is basically acting as its own mailman. It doesn't need to hand your sensitive subscriber data over to a third-party marketing platform.
That's huge for privacy.
It is a unified theory of operation applied to every single medium. And it executes all of this with deep infrastructure awareness. For example, the system intelligently monitors the configured network endpoint.
What does that mean in practice?
Well, if it detects a local IP address, specifically 127.0.0.1, which is the universal address for this exact computer, it will proactively attempt to auto-start the local Llama engine for you.
Oh, that's clever.
But if it detects an external IP, it recognizes that it's talking to another machine entirely and skips the auto-start. It deeply understands its environment.
Okay, but to pull all of this off, text synthesis, image generation, embeddings, language translations to truly operate independently without the cloud, a system needs its own localized resources.
It needs raw data.
Exactly. It needs a massive vault of data sitting right there on the hard drive. And the source code shows us exactly how much SYRAG is hoarding offline to make this illusion of independence a reality.
The setup offline models.py script details exactly what that offline footprint looks like.
And it's big.
Very big. It downloads about 5.5 gigabytes of models to store permanently on the machine. That includes the BAII embedding models, which take up about 420 megabytes, and the Argos Translate models, which cover 10 different language pairs and take up around 5 gigabytes.
I want to define embedding models quickly for you listening. When we talk about AI reading documents, it doesn't read English or Spanish. It reads math.
Right, numbers.
Embeddings are the tools that translate human words into mathematical coordinates so the AI can understand relationships between concepts. So you're saying it downloads 420 megabytes just for that translation dictionary?
Yes.
I have to push back here. A 5.5 gigabyte footprint just to run translations and math conversions offline. That is a pretty heavy lift for a standard laptop hard drive.
It's not small.
Especially when making an API call to a cloud translation service is practically weightless. It takes 0 hard drive space to just ping the cloud.
It is absolutely a heavy lift. 5.5 gigabytes is a significant chunk of storage. But if we connect this to the bigger picture, this is the literal physical price of true independence.
The cost of doing business offline.
Exactly.
Yeah.
You have to ask yourself what you are actually buying with those 5.5 gigabytes of space. You are buying 0 dependency on external corporate registries at inference time.
Right.
You are buying the mathematical guarantee that your highly sensitive internal documents can be embedded, searched, and translated into Italian, German, French, or Spanish without a single byte of that proprietary data ever leaving the silicon of your physical hardware.
Wow.
In this architecture, the cloud becomes a luxury option, not a fundamental requirement.
And all of this independent state, all these massive files and processes are kept perfectly aligned across the entire platform.
Through the sector manager.
Yeah, the dashboard sector manager.py file uses a robust database called PostgreSQL to synchronize the state across the core, the ecosystem, and the web dashboards.
And its fail-safes too.
It does. Again, following that hospital generator logic, if the database drops, it doesn't crash. It falls back to a local memory cache and gives the user clear visual indicators on their screen.
Right, the color coding.
Green if everything is synced to the database, orange if you are running on the offline cache, and red for a critical error. It's observability designed right into the architecture.
The LLM flexibility we see in SYRAG isn't just an isolated parlor trick. It lives inside this meticulously synchronized, deeply monitored, and rigorously tested architecture.
So as we wrap up this deep dive into the raw blueprints of SYRAG, let's synthesize what we've actually uncovered in the kitchen today. We found that this system enforces agnosticism and data governance on 3 distinct levels.
Level 1 is architecture. The core's LLM interface defines a strict local-first hierarchy. Policy is written as code. There's absolutely no silent cloud fallback.
No cutting corners.
Right. Level 2 is resilience. The LLM manager provides a robust 5-step fallback chain, allowing services to degrade cleanly from your GPU down to your CPU, all the way down to a raw offline search.
And the final level?
Level 3 is integration. This local-first philosophy isn't just for text chatting. It is synchronized across the dashboards and extended consistently to complex tasks like image generation and independent newsletter distribution.
For you listening, understanding how this architecture actually works gives you a real superpower.
It really does.
Because the next time you hear a slick pitch for a new AI tool, you now have the vocabulary to look past the menu. You can distinguish between platforms that merely promise privacy in their marketing copy and platforms that mathematically enforce it in their code.
The code we reviewed today proves definitively that a fully local, governable AI ecosystem isn't just some theoretical proof of concept for the distant future. In systems like SYRAG, it is the default operational state today.
It really brings us right back to where we started, the glossy menu versus the health inspector's report.
The marketing versus the reality.
Exactly. We've spent this time walking through the kitchen, looking at the heavy blast doors, the cascading backup generators, and the massive 5.5 gigabyte offline vaults. So I want to leave you with a final thought to mull over.
Okay.
We've just seen that open source local systems can mathematically guarantee privacy and run complex AI on messy everyday hardware. So why are multi-trillion-dollar tech companies insisting that true, helpful AI requires your personal data to be constantly processed in their massive centralized clouds?
That's the real question, isn't it?
Yep. Are they actually restricted by the limits of technology? Or are those cloud-only architectures driven entirely by the needs of their business models? Next time you are using your favorite private AI tool for work, ask yourself, if your local network briefly drops, does the system gracefully pause, or does it silently phone home to a cloud server to finish your thought without telling you?
What is its default state?
Exactly. Are you just reading the menu they handed you, or do you finally know what's happening in the kitchen?